So in this latest video on AS statistics, we'll be looking at and introducing binomial probability. So for a situation to be described using a binomial model, we must have four conditions, and those four conditions are the following. So we must have a finite number of n trials being carried out. The trials are independent. The outcome of each trial is deemed as either a success or a failure, and the probability P of a success outcome is the same for each trial. So what I'm going to do now is just go through what we actually mean by each of those four things. So for there to be a finite number of trials, basically you can't change the number of trials that you are having. So for example, if you say you're having 10 trials, you have to complete all 10 regardless of what the outcomes of each of those individual trials are going to be. The trials need to be independent, so in other words that the outcome of one trial cannot have an impact on another. The outcome of each trial is deemed as either a success or a failure. Now this translated basically means that in order for you to have a binomial model, you can only have two outcomes. So for example, which will lead on to a couple of examples later, is that if you are throwing a coin, yes, the two outcomes you can have when you throw a coin is going to be a head or a tail, but you can class that as either being a head or not a head. So therefore a head would be a success, not head would be a failure. If you're rolling a die, you wouldn't necessarily look at each individual number because there you've got 6 different outcomes. However, you could say that if you're wanting to roll a 5 and not a 5, then a 5 would be a success, not a 5 would be a failure. So this only works when you've got 2 possible outcomes in the whole entire event. And finally, the probability of a success has to be the same for each trial. So this kind of links in with the whole aspect of being independent, is that the probability can't change for each individual trial that you then do. So let's have a look at an example to kind of relate this to. So here we've got an example of if a coin is thrown 5 times, what is the probability of getting at most 3 tails? Now before we go on to answer this particular question, we kind of relate this particular issue to a binomial model. And the reason how we can connect it to a binomial model is because it satisfies those 4 conditions. So here we've got a fixed number of trials, which is 5, so we're definitely going to throw this coin 5 times. The outcome of each trial is going to be independent of each other. So for example, the outcome of my first throw is not going to have an impact on my second, my third, my fourth or my fifth. I've only got 2 possible outcomes I can have, so either a tail or not a tail, or a head even. So I've only got 2 possible outcomes, and the probability of a success, which in this case, because we're focusing on tails, is fixed, so it's always going to be a half. Now when you have established that a particular experiment follows a binomial model, what we can say, and this is really important that a lot of students tend to forget, is we can use this notation to simplify the parameters of that particular model. So here we've got x is deemed to be binomially distributed with n number of trials and the probability of success being p. So reading into this particular example, here we've got x, which is the roll of the die, is assumed to be using a binomial model, and here we've got a fixed number of trials, which is 5, and the probability of a success, which in this case is a tail, is a half. And this is how we would start and go about answering this particular question. So the next thing we're then going to do is look at how we go about answering this question. So here what I've done is I've written down all the possible outcomes of throwing a coin 5 times, and because we're focusing on and counting the number of tails, I've kind of separated it and I've done the outcomes in a systematic fashion to write down all the possible outcomes. So here, as you can see, we've got a total of 32 possible different outcomes we can have on these 5, and the first column represents 0 tails, in which I've got 1 possible outcome. The second is 1 tail, in which I've got 5. The third column is 2 tails, so here I've got 10 different possibilities. The next one is 3, in which again I've got 10 possible different outcomes for a combination. Let's say the fifth one is for 4 tails, which I've got 5, and for 5 tails I've got 1 possible outcome. Now if you've looked at these numbers, should kind of ring alarm bells, especially if you've already looked at binomial expansion, which will lead into after. So there is a possible way that we could find out those numbers, or those numbers might ring a bell in due course, especially if you've looked at Pascal's triangle. So let's go about answering this question. So again, we're looking at getting at most 3 tails. So I'm looking for, in terms of applicable sort of combinations, I'm looking for each of the first, and if I just highlight all of these columns are satisfying the condition in the question, and just making sure I'm actually highlighting them like so. So from this, what I can then do is, what I then need to do is work out what each of these probabilities are. So I can either get 0 tails, 1 tail, 2 tails, or 3 tails, or being the operative word. So here, if I work out the probability of this, now the key thing I notice is that the probability of each of these rows is going to be the same. So here I've got 0.5 times 0.5 times 0.5 times 0.5 times 0.5, and that is a probability. Even though I've got different letters and different outcomes, that is a probability for every single one of these highlighted sort of outcomes, and in total I've got 26 of those. So rather than adding up each individual sort of row, what I can do is be a little bit smart about this, and I've got, well, if each row is the same calculation or same probability, then all I need to do is times that by 26, and if I type that into my calculator, which I'm going to do now, so 26 times 0.5 times 0.5 times 0.5 times 0.5, etc., I get the answer of 0.8125, and there is my final answer. Now, some of you may have calculated this in a slightly different way, and it might be pure on coincidence, but this is the correct thinking behind it, is as we notice that every single sort of row has the same probability, because the probability of a success is the same as a probability of a failure, then technically what I could do is I could work out the probability using just the basic rule of probability, and that is how many outcomes satisfy the condition. Well, that's 26 out of 32, which simplifies to be 13 over 16, and if I type that into my calculator, convert it into a decimal, I get the same answer. Now, this method of counting the outcomes over the total number of outcomes only works if the probability of a success is the same as the probability of a failure. In other words, that every single row, if the probabilities are exactly the same, and in some cases they might be, then yes, I can look at the total number of combinations being divided by the total number of applicable outcomes or combinations, in which I could get the correct answer. So if we look at another example, so in this particular case we've got a die and it's being rolled 5 times. What is the probability of getting exactly 2 6s? So again, just like before, what we're going to do is we're going to write down all the possible outcomes that we can have when we roll a die 5 times and looking for exactly 2 6s. So here a 6 is a success, and that has a probability of 1 over 6, and not a 6 is classed as our failure, and that has a probability of 5 over 6. So again, I've listed all the possible outcomes using a systematic system of writing out all possible, and I can see that I've got 10 different combinations. Now, in terms of what I notice when I'm actually writing down the probability, so here looking at the first one, I've got 6 times a 6 times 5 6 times 5 6 times 5 6, and let's say I pick another row, so let's go for this one here. So I've got 6 times 5 6 times 5 6 times 5 6 times a 6. Let's pick this row here, so I've got 5 6 times 1 6 times 5 6 times 5 6 times 1 6, and finally at the bottom I've got 5 6 times 5 6 times 5 6 times 1 6 times 1 6. So what do I notice? Well, I notice that for each particular row the probability is going to be the same, and the reason for that is because in each particular row I've got the same number of successes as I have failures. The only thing that's different is the order in which those successes and failures come in. So each particular row satisfies this particular column, in terms of working out. So in every single row I'm going to have the number of successes, the probability of success, to the power of how many successes I want. Successes wanted, and that's going to be multiplied by the probability of a failure to the power of how many failures I want. And obviously then, because I've got 10 different combinations, what I then need to do is multiply all of that times by the number of qualifying combinations, which in this case is going to be 10. So to work this particular question out, what I need to do is I need to do 10 times 1/6 to the power of 2 times 5/6 to the power of 3. And if I type that into my calculator, which I'll do on the screen, so I've got 10 times 1/6 to the power of 2 times 5/6 to the power of 3. Press equals, I get the exact answer of 625. So 625 over 3, and let's get the calculator up again. 888. And if I was to write that as a decimal, try and keeping your answer to 3 significant figures if it doesn't specify, but it's always good practice for you to write down what you rounded up to. So I'm going to go for 0.161 to 3 sig fig, and there is my final answer. But even as a fraction form, that would be absolutely fine. So the key thing to note is actually if each of the rows for every single possible combination is going to be the same, then really the difficult thing, or the most time consuming thing I need to do, is find out exactly how many different combinations I'm going to find. Now, depending on how many trials you've got and how many successes you want, that can be very, very time consuming. So what we need to try and do is see if there is a much quicker way of finding out how many different combinations I've got with n number of trials and x number of sort of successes, then I could massively speed up the process of working out these types of questions. But more importantly, I won't actually need to write down all the combinations or list all of them out. Now, thankfully, a formula of that sort of capacity does exist. So as I mentioned, so if we can find the total number of qualifying combinations, writing down all the combinations is not going to be necessary, it's going to be unnecessary. And the formula to find out the total number of combinations of our successes after n trials is using the formula that you can see on the screen. So here what we've got is n represents the total number of trials, and r, which is sometimes known as x in some websites, some revision guides and some textbooks, is basically the number of successes. So if you look back at the previous particular question, here we had n equals 5 and we were looking at 2 successes. So then typing this into our calculator, I'd do 5 factorial over 2 factorial and then 5 minus 2 factorial. And again, if I get the calculator out like so, I can enter this formula in. So I set my fraction, I've got 5, and then use the factorial button, which is just on the inverse x button. Scroll down, I've got 2 shift factorial bracket 5 minus 2, I could just enter 3, and then factorial equals 10. So you can see that gives me 10 combinations. And like so, if I go back, that's exactly how many different combinations I had over here. So you can see I've got a list of 10 different possible outcomes where I'm out of 5 trials, I'm having exactly 2 successes. Now, in terms of learning the formula, this used to be given in the formula book, is actually a pre-programmed function on your scientific calculator. Now, on your scientific calculator, you should find that you've got this NCR function. And so if I get the calculator back up, which is the calculator most of you will probably most have, is you can see that the NCR function is a shift function above the division symbol. Now, how we enter this is usually in the format of NR. So here, if we're going to enter, let's say this situation here where we've got 5 trials with 2 successes, I'm going to enter 5, then press shift and then division button, little c comes up, and then enter 2 equals, and that tells me I've got 10 combinations. So if I wanted, let's say I had 12, let's say for 15 trials, and I wanted to know how many different combinations are out of 15 trials are you going to get exactly 8 successes, then the answer would be 6,435 different combinations you would get. Now you can imagine you trying to write that down, you're going to be there forever. So this is why using this calculator and understanding this particular format is going to be a lot easier and a massive time saver, rather than you listing all the possible outcomes in a form of a list or a sample space diagram. So to summarize, when a situation is classed as being a binomial model, we can use the following formula to find the probability of the number of x successes with a probability of p out of n number of total trials. Now, when you are starting any binomial distribution question or a model that's deemed to be binomially distributed, it's really important you always start off by writing this. So like I said, x can be is just the name of the experiment, but you can assume that it's binomially distributed, and then how you want to write this down is n is the total number of trials and p is the probability of a success. So you finding out the probability of x number of successes is then what we then need to do is this nx is basically ncx. This part here is basically the probability of a success to the power of the number of successes. And if we get a different colour, this here is basically the probability of a failure. So if p is the probability of a success, 1 minus p will be the probability of a failure, and that's basically to the power of the number of failures, which, if we're having n number of trials, take away the number of successes, which is what n minus x means, that will then give us the number of failures. And this is the general formula that you need to remember when you're working with binomial distribution probability questions, like so. It's definitely something that I definitely do recommend you making a note of. So let's now have a look at some actual examples, very similar to what we've done. So in this particular example, a bag contains 3 blue and 7 red marbles. A marble is selected at random and the colour is noted and then replaced back into the bag. If this is repeated 10 times, find the probability of getting exactly A, 4 red marbles, B, less than 2 red marbles, C, more than 7 red marbles. So for this, the first thing we need to do is set up the parameters of this particular question. So in this, we've got x, which is you selecting a marble out of this bag, is binomially distributed with a total number of 10 trials, and the probability of a success. Now here we're only focusing on red marbles, so you selecting a red marble is what's going to be a success, and the probability of selecting a red marble is 7 out of 10, like so. So from this, what we then want to do is then use the formula to work out these questions. Now we can only use the formula for exact values, so here in part A, that's exactly what we're going to do. So in part A, we've got n equals 10, p equals 0.7, and x equals 4. So what I'm going to do is I'm going to substitute that straight into the formula. So here I've got 10 and I've got 4 times 0.7 to the power of 4 times the probability of a failure, and n minus x, which in this case is going to be 6. So now if I get the calculator out and I type that all into my calculator, so here I've got 10 NCR 4 times 0.7 to the power of 4 times 0.3 to the power of 6, press equals, and it comes up with a probability of 0.0368 to 3 sig figs, so 0.0368 to 3 SF, like so. Now for B, B is looking for less than 2 red marbles, so here we're looking for either 0 red marbles or 1 red marble. So what I need to do is work out the individual probabilities of getting 0 red and 1 red, and then add the probabilities together. So let's get a different colour pen, so let's go for blue. So here, so when n equals 0, or when, should I say when x equals 0 rather, and that's basically for 0 red marbles. Here I'm going to have 10 0 times 0.7 to the power of 0, because I've got 0 reds, times 0.3 to the power of 10. And if I type that into my calculator, which I'll get out here, so here I've got 10 shift NCR 0 times 0.7 to the power of 0 times 0.3 to the power of 10. Then here it's going to be in standard form, so it's 5.9049 times 10 to the power of, and let's go back to -6. So now let's do when I get 1 red. So again I'm going to have 10 1 times 0.7 to the power of 1 times 0.3 to the power of 9 equals, and again using your sort of initiative, the powers need to both add up to the total number of trials. So that's just one way just to make sure that you've done it correctly. Now for this I'm just going to simply use my handheld calculator just to make it easier and a little bit quicker. It says times 0.7 times 0.3 to the power of 9, and I type the answer in and I get 1.37781 times 10 to the power of -4. Now if I then add those two calculations together, I'll get an answer of, so just enter that in, so 9.049 to the power of -6. I get a total answer of now the calculator's given to me in standard form, which is not really a problem, times 10 to the -4, so round this up to 3 sig fig, I'm going to get 144, and that's to 3 significant figures. And then finally for C, now for C more than 7 red marbles, that's going to be where X, I'm looking for either 8 red or 9 red or 10 red. So here I'm going to have to do 3 different calculations. So if I just quickly get rid of all of this, and work through the notion of, or the model like I've got above. So here for C, I've got, so first of all let's work out what's probability of getting 8, so that's going to be 10 8 times 0.7 to the power of 8 times 0.3 to the power of 2, work that out, and then do 10 9 times 0.7 to the power of 9 times 0.3 to the power of 1, work that out, then do 10 10 times 0.7 to the power of 10 times 0.3 to the power of 0, and again if I work out each of those 3 values, which I'm going to do now, I'm going to get 0.23347440405. For the 9 combination, well 9 successes, I get an answer of 0.121060821, and for 10 successes I get a probability of 0.0282475249, and then all I then need to do is add up each of those 3 probabilities and I get an answer of 0.3827824864. So rounding that answer up, I get 0.383 to 3 sig fig. And there we go. Now, a common question you might ask is, do I need to write down all the exact value in each of these particular ones here? Now, to make your answer as accurate as possible, yes, But generally speaking, if you know you're going to round your answer up to 3 sig fig, then generally speaking, all they need to do with these numbers is maybe write them to 5 sig fig. So as long as you go that little bit extra and a couple of digits extra than how you're going to envisage writing your final answer, then you should come out with the same answer. But like I said, if you can try and keep it with fractions, brilliant. But obviously, looking at the size of the numbers you can get, it's unlikely that your calculator will give you a fractional answer. But like I said, as long as you're going that little bit extra than however you're going to round your answer up, you're going to be absolutely fine, and you shouldn't lose any marks in terms of accuracy. So let's have a look at the second example. So here we haven't got a big waffle of a story, but we can kind of get the gist of translating what this question actually is. So here what I've got is I'm doing it's binomially distributed. I've got a total of 12 trials, and the probability of success is 0.35. So this is the probability of a success, and the 12 is the total number of trials. So for this, for part A, which I'll do in green, we're going to work out the probability that x equals 9. So I don't need to write down the binomial sort of notation because it's already written in the question, so that's going to be absolutely fine. So if I do A here, so here I'm looking out of 12 trials, exactly 9 successes. I'm going to multiply that by the probability of success, which is 0.35, times the power of 9 rather, times the probability of failure, which will be 0.65, and that's going to be to the power of 3. And if I type that into my calculator, which I'll do now, so typing this in, I've got 12 NCR 9 times 0.35 to the power of 9 times 0.65 to the power of 3. Oh, it's come out wrong on the calculator, it's going to be looked up. It's the power of 9 times 0.65 to the power of 3, and just double check that seems fine, and I get an answer of 4.7, let me just load that up again, 6184, and that's times 10 to the power of minus 3 or minus 4, minus 3. So this translated is going to be 0.00476 to 3 significant figures, and there is my final answer. Now for B, which I'll do in red, so here I'm looking for where x is less or equal to 2. So here I'm looking for when x is 0, when x is 1, and when x is 2. So for this I've got to do, let's go for when x is 0. So here I've got 12 0 times 0.35 to the power of 0 times 0.65 to the power of 12, and I'm going to add that to 1 success times 0.35 to the power of 1 times 0.65 to the power of 11 plus, and then 2 successes times 0.35 to the squared times 0.65 to the power of 10. Now typically, depending on how competent you are with working with your calculator, I could enter all of that in one row to save me a bit of time, and also means I don't have to round up any intermediary answers. However, when you look at mark schemes, now if I misenter a digit, I'll have no way of actually checking to see if any of this is right, and also I could lose marks because technically I could get 3 marks for working out each of those 3 individual probabilities. So it would be good practice for you to write down what the actual official answers should be. So working this one out, I get 0.005688 plus 0.036753 plus 0.108846, and if I add that all up together, I get an answer of 0.151287, which rounded up gives me 0.151 to 3 significant figures. And then finally for C, let's do this in blue. So more than 10, that's going to basically imply where x equals 11 or 12. So for C, all I then need to do is do 12 and 11 times 0.35 to the power of 11 times 0.65 to the power of 1 plus 1212 times 0.35 to the power of 12 times 0.65 to the power of 0. And if I work out each of those individual probabilities, we get, and type this into the calculator, we get 0.000075308 with a few extra digits. Typing in the probability for exactly 12 successes out of 12, we get 0.000337922, and if we add those probabilities together, we get a final answer of 0.0000786875636. Now the answer might be given on your calculator in standard form, so round this answer up, we get 0.0000787 to 3SF. And there is our final answer. Now, to practice these particular questions, there will be a worksheet attached in the description below, and in the next video I'll be showing you how to use the binomial distribution function that's on your menu screen on the Casio FX991EX calculator to make your life a heck of a lot easier when dealing with binomial distribution questions.